The solar system we think we know might be hiding one of the greatest secrets in modern astronomy. For over a century, scientists have been chasing whispers of a massive world lurking in the darkness beyond Neptune, a planet so distant that it takes thousands of years to complete a single orbit around the Sun. This isn't science fiction. This is the hunt for Planet 9. And after decades of searching, we may finally be on the verge of either confirming its existence or putting this cosmic mystery to rest forever. Our journey begins not with cutting-edge telescopes or supercomputers, but with a simple question that has haunted astronomers since the dawn of the space age. Is our solar system complete? For most of human history, we believed we knew all the major players in our cosmic neighborhood. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. 8 planets, each following predictable paths around our star. But what if there's a 9th world out there? A planet so far away that we've never seen it directly, yet so massive that its gravitational influence shapes the outer reaches of our solar system. The story of Planet 9 is really a story about gravity, mathematics, and the detective work that happens when astronomers notice something doesn't quite add up. It's a tale that stretches back more than 100 years, to a time when scientists believed they had discovered a 9th planet, only to realize decades later that they had been chasing a mathematical ghost. But recent evidence has reignited the search, and this time, the clues are far more compelling. To understand why scientists think Planet 9 might exist, we need to travel to the edge of the solar system, far beyond the realm of the major planets, to a region where sunlight is barely distinguishable from starlight. This is the domain of the trans-Neptunian objects, a vast population of icy worlds that orbit in the cold darkness beyond Neptune's path. These objects are the remnants of our solar system's formation, frozen relics from a time when the planets were still taking shape. Most of them are small, irregularly shaped chunks of ice and rock, but some are large enough to have names and orbits that astronomers track with great interest. In the early 21st century, astronomers began cataloging these distant objects with unprecedented precision. They discovered that many of the most distant trans-Neptunian objects share a peculiar characteristic. Their orbits are clustered in ways that seem statistically improbable. Imagine throwing a handful of marbles across a room and finding that most of them end up in the same corner, even though you threw them randomly. That's essentially what astronomers were seeing in the outer solar system. A group of objects, each taking thousands of years to orbit the Sun, all seem to have their closest approaches to the Sun pointing in roughly the same direction. This clustering wasn't supposed to happen. In a solar system governed purely by the gravity of the Sun and the 8 known planets, these distant objects should have orbits that point in all different directions, scattered randomly like leaves blown by the wind. But they don't. They're organized in a way that suggests something massive is out there, something with enough gravitational pull to herd these objects into similar orbital paths. The first major hint came from an object called Sedna, discovered in 2003. Sedna is a world about half the size of Pluto, but its orbit is extraordinarily strange. At its closest approach to the Sun, Sedna is still farther out than Neptune, and at its most distant point, it travels more than 900 times farther from the Sun than Earth does. An orbit like that shouldn't exist in our solar system unless something else influenced it. The Sun's gravity alone can't explain why Sedna is on such an elongated path, and none of the known planets could have placed it there. For years, Sedna remained an anomaly, a puzzle piece that didn't fit the picture astronomers had of the solar system. But then more objects were discovered with similarly bizarre orbits. In 2014, astronomers found an object called 2012 VP 113, which also had an extremely elongated orbit that kept it far from the Sun. Then came 2013 RF 98, and others followed. Each new discovery added weight to the idea that these weren't just random oddities, but rather pieces of evidence pointing towards something much larger. By 2015, 2 astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, decided to investigate this clustering more rigorously. They ran computer simulations to test whether the orbits of these distant objects could be explained by chance alone. What they found was striking. The probability that these orbits were randomly arranged was extremely low, less than 1%. The clustering was real, and it demanded an explanation. Batygin and Brown proposed a solution that was both elegant and audacious. What if there was an undiscovered planet out there, a world much larger than Earth, orbiting the Sun at an enormous distance? If such a planet existed, its gravity would naturally shepherd the trans-Neptunian objects into the clustered orbits that astronomers were observing. The math worked beautifully. A planet roughly 10 times the mass of Earth, orbiting at an average distance of about 600 times farther from the Sun than Earth does, could explain all the observed clustering. This hypothetical world was dubbed Planet 9, and the scientific community took notice. Here was a testable prediction, grounded in solid observational data and backed by rigorous mathematical modeling. If Planet 9 existed, it would be one of the most significant astronomical discoveries in over a century, fundamentally changing our understanding of the solar system's architecture. But proposing the existence of a planet is one thing. Finding it is something else entirely. Planet 9, if it exists, is so far away and so faint that detecting it would be like trying to spot a black cat in a coal cellar at midnight. The planet would be too distant to reflect much sunlight, making it incredibly dim even through the most powerful telescopes on Earth. Astronomers estimate that Planet 9 could be magnitude 22 or fainter, which means it would be about 25,000 times dimmer than the faintest stars visible to the naked eye. Searching for such a faint object requires both patience and precision. Astronomers can't just point a telescope in a random direction and hope to stumble upon Planet 9. They need to narrow down the search area, which means refining their predictions about where the planet might be based on the orbits of the trans-Neptunian objects. This is where the real detective work begins. The orbits of the distant trans-Neptunian objects act like breadcrumbs, each one providing a clue about where Planet 9 might be hiding. By analyzing the specific ways these orbits are tilted and elongated, astronomers can construct models that predict the most likely location of the unseen planet. It's a bit like trying to find someone who's hiding in a vast forest by looking at the footprints they left behind. You can't see the person, but you can follow the trail. Over the past several years, Batigan, Brown, and other researchers have refined their models again and again, incorporating new data as more trans-Neptunian objects are discovered. Each new object adds another constraint to the models, helping to narrow down the possible locations for Planet 9. The process is painstakingly slow because discovering these distant objects is itself a major challenge. They're faint, they move slowly across the sky, and they're easy to miss among the countless stars that populate the background. Yet despite the difficulties, the search has been relentless. Multiple observatories around the world have joined the hunt, dedicating precious telescope time to scanning the regions of the sky where Planet 9 might be lurking. The Subaru telescope in Hawaii, one of the most powerful optical telescopes on Earth, has been a key player in this search. Its wide field of view and exceptional sensitivity make it ideal for surveying large swaths of the sky in search of faint, moving objects. As the search has progressed, some tantalizing candidates have emerged. Every so often, astronomers spot a faint point of light that moves just slightly between images taken on different nights, a telltale sign of a distant object orbiting the Sunday. Each candidate is subjected to rigorous follow-up observations to determine whether it's a genuine trans-Neptunian object or just a background star or galaxy. Most of the time, the candidates turn out to be false alarms, but occasionally they reveal new members of the trans-Neptunian population, adding more data to the ever-growing catalog. But here's where the story takes an intriguing turn. As astronomers have discovered more and more distant objects, the evidence for Planet 9 has both strengthened and become more complex. Some newly discovered objects fit the clustering pattern perfectly, reinforcing the idea that an unseen planet is out there. Others, however, have orbits that don't quite match the predictions. This has led to a vigorous debate within the astronomical community about whether Planet 9 really exists or whether the clustering could be explained by other means. One alternative explanation is that the clustering is a statistical fluke, an artifact of observational bias. The argument goes like this: astronomers can only find these distant objects when they're near their closest approach to the Sun, because that's when they're brightest. If the surveys that discover these objects are concentrated in certain parts of the sky, then the clustering we see might not reflect a real physical phenomenon, but rather the limitations of where we've looked. In other words, maybe we're seeing a pattern that isn't really there, like seeing shapes in clouds. This is a serious concern, and astronomers have taken it into account. They've carefully analyzed the observational biases in the surveys that discovered these objects, trying to determine whether the clustering could be a product of where and when the sky was observed. The consensus among most researchers is that while observational bias certainly plays a role, it's unlikely to fully explain the degree of clustering that's been observed. The pattern is too strong and it persists, even when accounting for the biases. Another alternative explanation involves a very different kind of object, a primordial black hole. What if, instead of a planet, there's a tiny black hole lurking in the outer solar system? A black hole with a mass of several Earths would be incredibly small, perhaps no larger than a grapefruit, but it would exert the same gravitational influence as a planet of the same mass. The idea is speculative, but it's not completely far-fetched. Some cosmological models suggest that small black holes could have formed in the early universe and survived to the present day. If one of these primordial black holes happened to be captured by the sun's gravity billions of years ago, it could be responsible for the clustering we see. The primordial black hole hypothesis is fascinating, but it's also difficult to test. Unlike a planet, which reflects sunlight and can be detected with telescopes, a small black hole would be completely invisible. The only way to find it would be to detect its gravitational influence on nearby matter, perhaps by looking for the X-rays emitted by material falling into the black hole. So far, no such signals have been detected, but the search continues. Meanwhile, other researchers have proposed that the clustering might be caused not by a single massive object, but by a disk of smaller objects, collectively exerting a gravitational influence on the trans-Neptunian population. This idea has gained some traction, especially among astronomers who are skeptical of the Planet 9 hypothesis. The disk model suggests that there are many more trans-Neptunian objects out there than we've discovered, and their combined gravity could, in principle, produce the observed clustering. However, this model has its own challenges. For the disk to produce the necessary gravitational effects, it would need to contain a substantial amount of mass, equivalent to several times the mass of Earth spread out over a huge region of space. Whether such a disk exists, and whether it could remain stable over billions of years, is a matter of ongoing debate. As the debate has unfolded, one thing has become clear. Resolving the question of Planet 9's existence will require more data. Astronomers need to discover more trans-Neptunian objects, especially ones with orbits that extend into the regions where Planet 9 is predicted to be. Every new discovery adds another piece to the puzzle, helping to refine the models and narrow down the possible explanations for the clustering. This is where new technology comes into play. In the coming years, a new generation of powerful telescopes will come online, promising to revolutionize our ability to search for faint objects in the outer solar system. The Vera C. Rubin Observatory, currently under construction in Chile, is perhaps the most anticipated of these new facilities. Once operational, the Rubin Observatory will conduct the most comprehensive survey of the night sky ever attempted, imaging the entire visible sky every few nights and cataloging billions of objects. Its unprecedented depth and coverage will make it a game-changer for the search for Planet 9. If Planet 9 exists, the Rubin Observatory will almost certainly find it within a few years of beginning operations. The telescope's ability to detect faint, moving objects will allow it to spot even the dimmest trans-Neptunian worlds, filling in the gaps in our current catalogs, and providing the data needed to either confirm or refute the Planet 9 hypothesis. And if Planet 9 doesn't exist, the Rubin Observatory will help astronomers understand what else might be causing the clustering, whether it's a disk of smaller objects, observational bias, or something we haven't yet imagined. But the search for Planet 9 isn't just about finding a new planet. It's about understanding the history and architecture of our solar system. The outer solar system is a relic of the chaotic early days, when the planets were forming and migrating through the protoplanetary disk. The distribution of objects in this region holds clues about how the planets formed, how they moved, and how the solar system settled into its current configuration. If Planet 9 exists, it would tell us something profound about the solar system's past. The planet's enormous distance from the Sun suggests that it didn't form where it is now. Instead, it likely formed much closer to the Sun, perhaps in the same region where Uranus and Neptune formed, and was later ejected to the outer reaches of the solar system by gravitational interactions with the other giant planets. This scenario is consistent with models of planetary migration, which suggests that the giant planets didn't stay in their original positions, but rather moved around significantly during the solar system's early history. The idea that Planet 9 might be an ejected planet adds another layer to its story. If true, it means that our solar system once had a different configuration, possibly with more giant planets than we see today. Some of those planets might have been ejected entirely from the solar system, sent into interstellar space to wander the galaxy forever. Planet 9, if it exists, would be a survivor of that chaotic era. A world that was nearly lost, but managed to cling to the sun's gravitational influence at the very edge of the system. This brings us to a broader question. How common are planets like Planet 9 in other star systems? Exoplanet surveys have revealed that many stars host planets in orbits that are very different from anything in our solar system. Super-Earths and mini-Neptunes, planets with masses between that of Earth and Neptune, appear to be extremely common around other stars. Yet our solar system doesn't have any planets in this mass range. If Planet 9 exists and turns out to be a super-Earth, it would suggest that our solar system is more typical than we thought, and that the apparent absence of such planets is just an accident of where we happen to live. On the other hand, if Planet 9 doesn't exist, it would mean that our solar system really is unusual in lacking these intermediate-sized worlds. This would raise interesting questions about why our system turned out differently from so many others. Was it just chance, or were there specific conditions during the solar system's formation that prevented super-Earths from forming close to the sun? These are the kinds of questions that drive astronomers to keep searching, even when the odds seem daunting. The hunt for Planet 9 has already taught us a great deal about the outer solar system, revealing a complex and dynamic region that's far more interesting than anyone expected. Regardless of whether Planet 9 turns out to be real, the search has expanded our understanding of how planetary systems evolve and how hidden worlds can shape the structure of the space around them. Now let's talk about the technical challenges of actually finding Planet 9. When you're searching for an object that might be 600 times farther from the Sun than Earth, you're dealing with light that has traveled for hours before it even reaches the object, and then hours more before it bounces back to your telescope. The faintness of such an object is almost incomprehensible. To put it in perspective, if Planet 9 is as far and as faint as current models suggest, it would take one of the most powerful telescopes on Earth several minutes of exposure time just to register a single photon of light reflected from its surface. This extreme faintness means that even if astronomers point their telescopes directly at Planet 9, they might not see it immediately. They would need to take multiple images over several nights or weeks, then carefully compare them to detect the planet's motion against the background stars. This is the same technique that was used to discover Pluto back in 1930, when astronomer Clyde Tombaugh painstakingly compared photographic plates to find a tiny dot of light that shifted position between images. But the modern search for Planet 9 is vastly more sophisticated than Tombaugh's search for Pluto. Today's astronomers use digital cameras with millions of pixels, automated software to analyze images, and powerful computers to simulate the orbits of hypothetical planets and predict where they should be. The process is still labor-intensive, but it's far more efficient than the methods available a century ago. One of the key challenges is distinguishing Planet 9 from the countless other objects in the sky that might look similar. At any given time, a telescope pointed at a random patch of the sky will see thousands of stars, galaxies, and asteroids. Most of these objects are either too bright or moving too quickly to be Planet 9, but sorting through them all requires sophisticated algorithms and a lot of patience. Astronomers look for objects that move at just the right speed, slow enough to indicate a distant orbit, but fast enough to be detectable over multiple nights of observation. Another challenge is that Planet 9's orbit is probably very elongated, meaning that the planet spends most of its time at vast distances where it's incredibly faint and only occasionally comes closer to the Sun, where it might be bright enough to detect. If Planet 9 is currently near the farthest point in its orbit, it might be so faint that even the best telescopes can't see it. This means that the search could take many years, possibly even decades, before the planet moves into a position where it's bright enough to be found. Despite these challenges, the search continues with remarkable dedication. Astronomers are driven by the knowledge that if Planet 9 exists, finding it would be one of the defining moments in the history of astronomy. The discovery would not only add a new member to our solar system's family of planets, but also validate decades of theoretical work and observational effort. It would be a triumph of human ingenuity and perseverance, a testament to our ability to uncover the hidden secrets of the cosmos through careful observation and rigorous analysis. But there's also the possibility that Planet 9 doesn't exist, and that's an important outcome too. Science isn't just about confirming hypotheses. It's also about ruling out ideas that don't match the evidence. If the clustering of trans-Neptunian objects turns out to have a different explanation, or if it's simply a statistical fluke, then the search for Planet 9 will have taught us valuable lessons about the limitations of our observations and the complexities of interpreting data from the outer solar system. In recent years, some astronomers have begun to express skepticism about the Planet 9 hypothesis, pointing to the lack of direct detection despite years of searching. They argue that if Planet 9 were really out there, we should have found it by now, given the resources that have been dedicated to the search. Others counter that the search area is enormous and that the planet could easily be hiding in a region that hasn't been thoroughly surveyed yet. The debate is healthy and reflects the scientific process at work, with researchers challenging each other's assumptions and pushing for more rigorous tests of the hypothesis. One intriguing development in recent years has been the use of citizen science to aid in the search for Planet 9. Projects like Backyard Worlds, Planet 9 have enlisted the help of thousands of volunteers to sift through astronomical images and look for faint, moving objects that automated algorithms might have missed. The idea is that the human eye is remarkably good at spotting patterns and anomalies, sometimes better than computers. By distributing the work among many volunteers, astronomers can cover far more ground than they could on their own. These citizen science efforts have already led to the discovery of several new brown dwarfs and other interesting objects. Though Planet 9 itself remains elusive, the projects have also helped to engage the public in the search, turning what might otherwise be an arcane scientific pursuit into a collaborative effort that anyone can participate in. It's a reminder that astronomy isn't just the domain of professional scientists. It's a field where curious minds from all walks of life can contribute to our understanding of the universe. As we look to the future, the question of Planet 9's existence remains one of the most tantalizing mysteries in modern astronomy. The evidence for the planet is compelling but not conclusive, and the search will likely continue for years to come. New telescopes, better data, and refined models will gradually narrow down the possibilities, bringing us closer to an answer. In the meantime, the hunt for Planet 9 has already enriched our understanding of the solar system in countless ways. It has revealed a dynamic and complex outer region where planets and smaller bodies interact in ways we're only beginning to understand. It has shown us that even after centuries of astronomical observation, our solar system still holds surprises, still has secrets waiting to be uncovered. Whether Planet 9 turns out to be a massive super-Earth, a primordial black hole, or a phantom conjured by statistical coincidence, the search for it represents the best of what science has to offer: curiosity, rigor, collaboration, and the willingness to follow the evidence wherever it leads. And that, perhaps, is the greatest discovery of all.